This video is about convolutional neural networks, or CNNs for short. Large neural networks can theoretically approximate any function. However, large networks often struggle to learn and to converge to good solutions. In this video, we use knowledge about the structure of the underlying problem to reduce the number of weights substantially. One example is the use of convolutional layers in computer vision. Whether an object is a bit to the left or right in an image usually does not make a big difference. It's still the same object. The convolutional layer can recognize an object independently of its exact position in the image. But what is it exactly, and how does it work? A convolution defines a filter W, sometimes also called a kernel. Given an input image X, we then slide this filter W over the input image X. For each position of the filter, the value for the output Y is calculated as the dot product of the filter and the part of the image that is covered by the filter. We then slide the filter to the next position. Let's look at an example. Assume that we have a grayscale image X with values from 0 to 255 and we want to detect vertical edges present in that image. For this, we use a so-called Sobel filter W. If we want the output Y to have the same size as X, we have to add some padding to X. For this, we will copy the outermost values to not introduce any new edges. To compute the output, we again slide the filter over the image. Each element is then computed as the element Y's multiplication of the overlap. The large values in the second and third column of the output Y indicate that there is a strong gradient between those columns in the image. In other words, a filter is a neural unit that processes information of every part of the image in the same way. That way it learns to recognize small recurring patterns. If you apply multiple filters after each other, stacking them, you give the network the capacity to recognize ever more complex patterns. We call this a convolutional neural network, or CNN for short. Such an architecture can be trained using backpropagation using, for example, mean squared error as loss. One simply needs to add up the gradients of the filter for every location the filter has been applied to. Compared to a fully connected neural network, a CNN has a significantly lower number of weights. It is generally also invariant to the position of a pattern in an image. This is called translation invariance. Pause the video to think why this is the case. CNNs are not constrained to two-dimensional inputs. To understand this, we first need to introduce the concept of a tensor. A tensor of order D is a d-dimensional array. It generalizes one-dimensional vectors and two-dimensional matrices to d dimensions. Now that we know what a tensor is, we can represent an RGB image as a three-dimensional tensor of shape, 3, height, width. We then need a three-dimensional tensor as a kernel which produces a two-dimensional output. This concludes convolutional neural networks. Thanks for watching this video.